I'm Tasha Halevi, and this is Footprint Radio. Daylight design technologies and strategies are making huge changes right now, and a focus on daylight will soon offer a much larger opportunity for energy savings in buildings than most designers are even coming close to tapping into. Not only does good daylight provide healthier, happier places for building occupants, but when done correctly, also can offer electricity savings anywhere from 25 to even 70%. Roadblocks such as high manufacturing costs, design costs, or even a general lack of understanding with install or user operation are quickly disappearing as materials become cheaper and technologies become smarter. One of our guests today, Rob Guglielmetti of NREL, will give us an in-depth understanding of daylight and daylight simulation that helps building designers design better. And later, BGBG member Mike Plann will share the green tip for easily improving your daylighting. But first, Konstantinos Papamichael joins us with his 30 years of in-depth study of daylighting. This is the Boulder Green Building Guild's Footprint Radio on KGNU Boulder, KGNU Denver. Konstantinos Papamichael, or Kosta, is a professor in the design program at the University of California, Davis and is the co-director of the California Lighting Technology Center at UC Davis. Konstantinos holds an architectural engineering degree, a master's in architecture with an emphasis in building science and minor in energy system engineering, and a PhD in architecture with major emphases in design theories and methods and minors in building science and computer science. He has been working on the development of energy efficiency strategies and technologies for buildings, focusing on fenestration systems and daylighting, as well as the integration of electric lighting and fenestration controls. Konstantinos participates in a wide range of academic and professional activities related to computer-aided design, daylighting, electric lighting, energy and environmental impact, and is author and co-author of over 80 related publications. Kosta, thank you for joining us today.
It's a pleasure to be here talking to you.
You've dedicated much of your career to a rather specific aspect of the building industry and daylighting technologies. What led you to dedicating your work to daylighting?
If you had asked me 30 years ago what would you do when you grow up, for sure I wouldn't say daylighting, research and lighting in research and business and controls in buildings. What happened is after I graduated from the Greek University and I got my degree and my license to practice, I decided to go for graduate studies because I realized I didn't know much about the building as a physical object. And when I arrived in Ames, Iowa, at Iowa State University, and I met with my major professor, he asked me what I wanted to specialize in. And I remember saying, but I'm an architect. I thought I should generalize. And he said, no, it doesn't work like that. You have to specialize. And I had to make a decision on what I want to specialize pretty fast. And thinking on my feet, I thought that the window may be the most important element in a building, connecting the exterior and the interior. So I said I would like to specialize on windows. And he suggested I take a course in daylighting. And initially I thought that he was kidding. And I remember asking him, what's there to learn about daylight? He said, a lot. And I'm still learning, and that's 30 years later. That was January of 1980 that this discussion took place. And then I came for a PhD at Lawrence Berkeley Lab, and I spent 20 years there truly learning quite a lot about daylighting. And I stayed there working with Steve and other folks there at LBNL for 21 years before I came here to UC Davis and setting up the California Lighting Technology Center with Michael Seminovich. So that's how I ended up doing daylighting. I was never planning on that.
In your experience with daylight, what are the greatest benefits of daylight?
Yep, that's a great question. Like, why do so much fuss about it? I see three types of benefits from daylight. Some of the most important is the psychological benefits, mainly through view to the exterior. The information that we get when we are indoors is extremely important for our health and well-being. Information about the time of the day, the weather condition, the state of the people is extremely important to keep us at a state where we can be calm and continue our work and our life. I remind my students sometimes that the ultimate punishment that our society has is to put you on a windowless cell. Then you have physiological benefits with respect to a light source. To start with, it gives us the part of the spectrum which is different during the beginning of the day, different during the middle of the day, and then at the end of the day, it changes what's called the color temperature. And it seems like, not it seems now, we know over the last 10, 12 years that the light, when it comes through our eyes, it follows two paths. One is the path that allows us to form images, and then there is another path that activates the whole circadian system of the body. It has an effect on all kinds of different substances and the way that our body releases it in the bloodstream, like melatonin, which regulates the sleep-wake cycle, or insulin, it's responsible for carbohydrates metabolism, or cortisol affects blood pressure, sugar levels. So that's the physiological effect, biological, if you like. Finally, there is a third group of benefits, if you like, the energy benefits, where you can switch or dim electric lights in daylit areas, and we can save like from 25 to 50% inside lit spaces, all the way to even more than 70% of the electric lighting energy in sky-lit spaces. And in addition to saving from electric lighting, we also save from cooling loads, especially during the summer, of course, when the electric lights are off, because electric lighting also contributes to the cooling load.
Your work starts to bridge the gap to create an interaction between daylight and electric light. Can you explain how today's daylight controls work and how you're working to bridge that gap that exists now?
The daylighting control strategy is a strategy that says, hey, if we have available daylight in a space, why use electric light? So the controls all have some means of estimating how much daylight is in the space, and then a controller that adjusts the electric lights accordingly. Now, there are two main mechanisms that we use to figure out when to start dimming lights or turn them off. One is the use of time clocks. We know when the sun rises and when the sunset is. Those are also pretty reliable and very inexpensive. The main problem with time clocks is that they don't know anything about weather conditions. So if it happens to have a heavy rainy day, at 11 o'clock your lights may go off and you won't be able to see. They don't understand the environmental conditions, the weather conditions, etc. Which brings us to the most effective way, which is the use of photosensors. You put a sensing device in the space that can sense how much light is in the space. The work that we have been doing here at CLTC in this area is to try to make these controls more reliable and more cost-effective. The technologies will always do what we want them to do. What fails is our lack of understanding about the conditions under which that system will find itself and what people will do to it. To give you an example, if we install a photosensor in the building in a space before the furnitures come in, and that photosensor is looking at a dark carpet, and then we calibrate it to work, and then we bring in the occupants, and the occupants bring in a white table and put it under the sensor, guess what will happen? All of the lights will dim down or even turn off, because now the sensor is not looking at a dark surface. It looks at a surface that's white, reflecting more light, and it thinks that there is more daylight in the space. We have come up with some pretty useful approaches of having the system automatically recalibrate themselves and be able to understand when these changes happen. You also have what I call the short-term changes, like people with different color clothing passing under the sensor. And depending on how close the sensor is and what the angular sensitivity of the sensor is, you may have a very, very strong effect on their signal. We have now developed systems that use two sensors, and we have one that runs very successfully in the West Sacramento Walmart here for many months now, and we have increased the reliability and the energy savings significantly.
So let's talk about some other exciting technologies out there that you're working on. Let's talk about smart glazing, smart windows, smart skylights.
This is a new area. I mean, it has been several years in the making. Today, I believe we have systems that truly make it out there, and we are very excited. We are working with these manufacturers to try and best understand how we can optimize performance. What these are, we also call them smart glazings or active glazings or dynamic glazings. And what it is, it's a glazing system that includes a component that allows variable transmittance on demand. So you have a system where you can turn a knob if you like, or you can send a small electrical input to it and change its transmittance from low to high. With respect to daylight, daylight does not follow the more the better paradigm, if you like. And this is, in fact, some of the mistakes that I have seen in inexperienced architects. They say, well, bring daylight, and they just overdo it. They bring way too much. If you bring too much daylight, you're going to bring glare with it, you're going to bring solar heat gain, etc. So after all of the lights are off, and it's 9:30 in the morning, for instance, if you start bringing more daylight into the space, then you start risking glare from the window, and you increase the solar heat gain, which contributes to cooling loads. So these dynamic windows, they allow you to vary the transmittance to optimize it for every time of the day. And early in the morning, you can have it at the highest transmittance to allow a lot of the less daylight that you have outside. And then as the electric lights start dimming down and then turning off, you start lowering the transmittance because you have so much daylight that a smaller fraction can satisfy the needs inside. So that's what the smart glazings are. They play the role of a window that adjusts itself manually or, in most cases, automatically using sensors to have the transmittance that's most suitable to optimize performance at any given time in the day. And actually, you can see it going for clear to a tinted state. The general term is the term chromogenic materials. Chromogenic materials come in two main categories, if you like. You have passive chromogenic materials, which fall into two categories that I know: the photochromic, that change their transmittance based on how much light falls onto them, and especially UV light. These are all of the sunglasses that we get that get darker when we go out in the sun. That's a chromogenic material. You also have thermochromic materials that change their transmittance based on temperature. Now, these are passive. They are pretty expensive to make. We cannot make them in window-size panes, if you like, but they are great for sunglasses. And then we have the active chromogenic materials, and I know three different technologies under that. One is the liquid crystals, which is a layer of liquid crystals, and you can change the transmittance from diffuse to clear. The next category is the electrochromic ones, which they include a thin film coating that it is applied to a glass or a plastic layer, and it changes transmittance from a high clear state to a low tinted state. And you can go from 3 to 4% at the low of transmittance at the low level up to 55 to 65% transmittance when you apply a voltage. And there is a third one that's called suspended particle devices, or SPD. And those are suspended particles in similar way to liquid crystals.
Pretty impressive technologies out there.
Very much. And we expect that we should see very increased levels both of comfort and of energy efficiency.
Well, it really sounds like we're at a very important point in time in terms of daylighting technology and design, and we're really making some huge leaps right now and into the future.
Yes, that's a very accurate statement, and it's a very, very exciting time to be a researcher in this area. So I feel pretty blessed that so many things are happening in the daylighting area, and we are finally making some good progress.
Rob Guglielmetti has been involved in lighting design in many different capacities. As a lighting designer for theater, electrical lighting designer and daylighting designer for museums, restorations, schools, office buildings, and more, Rob's focus now is on daylighting and simulation to promote sustainable building design. He is a researcher at the National Renewable Energy Laboratory, or NREL, where he focuses on applying daylighting simulation to improve building energy efficiency. Rob has presented daylighting strategies and technologies at conferences, including his recent workshop at Lightfair International 2010. Rob, thank you for joining us today.
Thanks, Tasha, for having me.
We hear a lot about the benefits of daylight, but what does that really mean?
Well, simple terms, if you do a good job daylighting and you control your electric lights to respond to that daylight availability and turn them off as much as possible, you can potentially save quite a bit of money in terms of your energy costs. Commercial buildings in this country use about 30 to 40% of their electricity on powering the lights. It's a very large slice of the electricity pie. So if you do a good job daylighting, you turn off your electric lights, there are going to be some dollars coming back into your pocket. Some of the other benefits are very, very important, but very, very difficult to put a dollar sign on. for example, retail sales improve in retail spaces that have daylight available to them. School test scores, there's a California study that showed that high school students scored higher on tests on average when those students were being tested and being educated in classrooms that had daylight, as opposed to students that were in a box with no windows and electric lights on all the time. Another important one is hospital patient rooms. Hospital patient rooms that are daylit tend to have patients that get sprung out a little bit sooner. These are benefits that are difficult to put down into a spreadsheet, but they are significant and they are tangible.
So when you're talking about wavelength and color temperature, is this really a scale that we look at in electrical lighting and in daylighting as well?
Well, there are different metrics for comparing different light sources and measuring light sources and the qualities of them. So you have things like color rendering index, which is imperfect, but it's at least an attempt to try to understand or quantify how well different electric light sources render color, for example. This kind of thing becomes really important to museum curators, for example, which is why daylighting is a huge component in museum design. A lot of the works that are in museums were created under natural light and only natural light, so it only makes sense to observe and appreciate those pieces of art under the same conditions, if you can. So many of the best museums in the world have very clever and inventive ways of introducing natural light into their galleries. But going back to the energy efficiency piece, daylight, sunlight, and skylight is essentially free light. We don't have to burn coal to produce daylight. It's happening far, far away from this planet. And if we can just bring it into these spaces and use it to our advantage, then we're doing a good thing.
All right, so let's finally get to your specialty, which is daylight simulation. Now that we all have a better understanding of what daylight really is about, what is it that you are doing when you're simulating, and what are the factors of daylight that you're simulating to get a result that building teams can apply? There
are simulation tools out there that allow us to simulate daylight, electric light, architectural spaces, etc. And this is the thing that for the last 17 years of my life I have been extremely interested in. I discovered a love for light when I was in college and designing with light, but I quickly saw that there were these tools available that would allow you to simulate the effects of light and lighting designs without actually hanging a light or plugging anything in or building anything. You could do it all virtually. And that was really appealing to me. So daylight simulation involves this exact idea that you would create a three-dimensional model of a space in the computer. And then you would basically import it into a software tool and describe to this software tool not just the three-dimensional architecture, but also what light sources are in the space and how are they arranged and where in the world is this building. And the computer can actually go, thank you for that information, and put the sun in the right spot and create a luminous sky hemisphere that accurately represents what is essentially a mathematical model for the brightness of the sky at that particular location on the planet. At that time of day, this technology exists, and actually the tool that I use almost every day in my work has existed for 20 years. It's called Radiance, and it's a light backwards ray tracing software tool is the technical term for it. And basically it solves that problem for you. You tell Radiance, I have this building and the walls are such and the windows are such and they let this much light in and the walls are painted white or green or whatever and they reflect this much light and there's a chair over here and there's partitions over here. And like I said before, you can tell it what time of day it is and what the sky conditions are outside. You could tell it whether it's sunny or if it's overcast or somewhere in between. And Radiance takes all that information in and essentially hunts around for light. The reason it's called light backwards ray tracing is that what's happening is you define a picture that you would like to see. You define basically a view, right, or an image plane, same as you would with a camera. And Radiance takes that scene and pixel by pixel, point by point, it traces paths from those points out into that scene that you created with your CAD tool. So these rays are simply it's just a mathematical process. If you use the analogy of the eye, if you describe a view of, here's my eye is sitting at this desk trying to look at this computer, and there's a window over here to my right, and I'm in this room that's 20 by 30 feet. Well, Radiance traces these paths from your eye into the scene, and those paths may intersect your desk, for example. Well, your desk isn't a light source. So once it hits the desk, it goes, okay, I've hit a desk, and it's eggshell white, and it's got this much reflectance, and it's not a light source. So now I need to trace more paths from that point again, looking for light sources ultimately. So from that intersection point, it traces more rays or more paths. And those rays go back out into the scene, and maybe one of them goes out through the window and actually intersects the sun that's out there. Now it knows, okay, I've hit the sun from this viewpoint. I'm able to hit the sun. The sun on this given day is this bright, and it's at this angle, and so it's emitting this many candelas per meter squared back towards that eye point that we started from. And so basically, a radiance image or a radiance simulation is the end result of literally millions and millions of these paths being traced, trying to find all of the light sources. And after it's found all the light sources, it also adds up all those other wonderful contributions that bubble up in a scene, in any scene, that are the end result of all the interreflected light, right? It's not just about the sun or the sky, but what happens when the sunlight hits that desk and bounces off the desk and lights up the ceiling and the walls and the people. So the end result of any image, even the image that you might see right now looking at your computer or looking out the window, is the end result of billions of photons that were emitted from light sources like the sun, the sky, and electric lights, and bouncing around into space and entering your eye and being transmitted to your brain.
Now that we understand what the daylight model does a little bit better, let's feed that back into something you spoke about earlier, which was the energy efficiency and how the daylighting can affect energy efficiency. Are there any good ways now with technology for the daylighting model to speak to the energy model?
Well, right now today, with a whole building energy simulation, you can look at all the interactions with all the mechanical systems. And most of these whole building energy simulation tools do incorporate some sort of a daylighting simulation component within them. But historically, the rigor of that calculation has not been very good. On the horizon, the work I'm doing at NREL right now is targeted at this deficiency. We are hard at work trying to apply the daylight coefficient approach and at the same time, we're trying to integrate them a little bit more tightly with Energy Plus and merge the results back together. So what we're trying to do is use radiance to do high-quality daylight simulation, understand what the electric lights would do in response to that daylight availability on an hourly basis over the course of a year, and sort of feed that electric lighting response, right, the dimming or the switching response, and feed that back to Energy Plus and let Energy Plus do what it's good at.
So on the horizon, we will see some more information for design teams.
That's the hope.
We've discussed the nitty-gritty of technologies, but how can you take advantage of good daylight now? BGBG member Mike Plann of Light Louver presents this week's Green Tip.
Everywhere I go, schools, office buildings, etc., I always notice that the shades are drawn over the top portions of the windows. Given that solar heat gain and glare can be a huge problem, this is an effective solution. However, the upper portions of your windows are actually daylight openings. The glass has a higher visible transmittance of light, and the purpose is to let more daylight into your building and reduce the requirement for electric lighting. When you have problems with solar heat gain and glare, it is effective to pull the shades, but once the sun is moved on, be a responsible user and open the shades back up to let that daylight back in. Alternatively, use a light shelf or even better, an optical daylighting device to drive daylight even deeper into the building. By following these simple guidelines, you can drastically reduce the requirement for electric lighting in your space, potentially saving energy and money. This has been your BGBG Green Tip with Mike Plann from Light Louver.
Thank you for joining us today on KGNU Boulder, KGNU Denver with Boulder Green Building Guild's Footprint Radio. You can podcast this show and learn more about the BGBG by going to bgbg.org or searching Footprint Radio on iTunes. BGBG supports many opportunities and events, including the 2010 Denver Boulder Solar and Green Homes Tour, September 25th and 26th. Please visit the Center for Resource Conservation or Colorado Renewable Energy Society websites to learn more about the event in your area. To share your green tip on the air, submit your ideas with our online forum on the Footprint Radio tab at bgbg.org or by emailing radio@bgbg.org. Thank you to our sponsors at the City of Boulder, Boulder County Business Report, Namaste Solar, and Boulder County for taking a step towards greener footprints. I'm Tasha Halevi. This is Footprint Radio.